in brackets fast, hopefully, and hopefully a little bit sort of understanding why certain decisions are made and the strategy behind that. So yeah, let's get going with some introduction and some context. So obviously the first is who am I? So I'm Laurence Hardman, as you may know, and I've sort of I've got three sides. So where's my presentation gone? I fly gliders quite a lot. I'm quite an enthusiast. I've been flying since I was about 14. I actively instruct students on a sort of ab initio basis and, sort of do the normal club instruction thing. And then I do also, on top of that, compete in local competitions in South Africa and hopefully a little bit more than that in the near future. Academically, I've got a background in computer science and mathematics. That's sort of enough of that. And then professionally, what I do pretty much to pay for my flying is I am a software developer and I specialize in sort of financial and analytical software. This point is also quite relevant, is who are you, the audience? So we've obviously had a bit of a shift in scope since the lecture sort of was first an idea. So initially we were looking at Macaulay's Gliding Club students. And yeah, so from there, we've actually sort of, our audience has broadened quite a bit. So now we're looking at the gliding community members. I believe some even international are joining in the talk. Primarily cross-country pilots and those looking to get a bit of an insight and edge on the basic strategy of cross-country performance. I must say, you're not going to beat Kawa just on my advice, but you are gonna have hopefully a better idea of sort of the numbers behind the cross-country flying. So yeah, what are we talking about? So this whole talk has actually got a sort of common underlying theme in that gliding competitions are competitions that are won by decision making. That's from GDEL. And there's a number of factors that influence these decisions. And obviously a good pilot will take all of them into account. So obviously the first one is the weather. That's unfortunately out of the scope of this lecture. We're not looking at the specifics of MET and sort of advanced soaring weather and stuff like that. There's also intuition, which is another pretty subjective factor, which we're going to eliminate from the scope. Technical knowledge and, well, your actual equipment itself, flying a good glider always helps, and knowing how to use it properly helps. And then the last sort of factor is the theoretical understanding of our decisions and on what we're doing. And that's really the focus of our talk. So yeah, we're trying to keep it independent of subjective specifics. There's some things that are very variable and depend quite a lot on irrelevant factors. So obviously gliders, instrumentation, weather, tasks, and luck is a very big one actually. And we'd rather focus on the pilot's informed decisions and the principles that aid them. So more actually why does a good pilot make certain decisions, as opposed to just what decisions does he make, and we kind of want to dig into that. So yeah, that's who we are and what we're talking about. And obviously, as with any hypothetical scenario, we do have to make some assumptions. So we've got a goal, and our goal is basically to fly a cross-country task as fast as possible. We're going to imagine ourselves in a typical competitive setting, and we're going to try and leverage our understanding of how we can optimize certain key factors that are common to almost all. Sorry, the chat's going absolutely mad. Let me see what's going on. There we go. Certain key factors that are common to all competition or all competitive scenarios. So we don't want to, talk just entirely about ridge flying or something like that, where that becomes irrelevant and sort of flatlands, low performance versus high performance gliders, things like that. So we're going to imagine ourselves flying in purely thermic, and actually best to imagine blue conditions where sort of, the weather isn't as much of a factor. And no teammates, that's another important one. Sort of having someone 10 k's ahead of you giving you advice is unfortunately not always going to be available. So yeah, there's that. And we're also sort of yeah, like that's pretty much just elaborating on what I said. Major decisions as a result of aircraft performance, teammate information, queue development, and wave need to be disregarded. They're out of scope. So now that we've sort of given ourselves some context, we can dive in and start looking at some of the underlying fundamentals of how we fly and uh, what the basic fundamentals are. So obviously, I think everyone knows what McCready theory is. I really don't want to spend too much time on this section. It's there is a lot of great material on the internet about McCready theory and sort of how it works and derivations and things like that. But basically, all of our decisions or all of our optimizations start with the base of normal McCready flying. And that is McCready, sort of flying McCready in itself is a very theoretical thing. And lots of people fly very fast without obeying it very strictly. But let's imagine ourselves in a situation where we are flying or sticking to McCready quite religiously. So what does McCready theory tell us? In essence, for a given day or a given task, we've got thermals of a fixed strength. And given that strength, we can refer to the polar curve of our glider to find a speed to cruise at in between the thermals that'll optimize our task speed or our cross-country speed. And additionally, we can also add some extra parameters to further improve on this. So if we're flying, or the vertical speed of the rising air we're cruising in is one of them, and head or tailwind component is another. Basically, what McCready tells us to do is three things. Strong thermals mean we need to fly faster. And we'll get to the reasoning behind all of this in a second, but these are basically the three golden rules. Strong thermals say we must fly faster. Sinking air also says we must fly faster, and if we're in rising air, we must fly slower, and flying faster into a headwind and slower with the tailwind. And in the next minute or two, you're going to see why this is the case and why this works. So yeah, using the polar curve. So basically, what is a polar curve? What does it look like? Again, don't want to spend too much time here. This is very basic subject, and you can also see I haven't had too much time to prepare. We don't have any fancy MATLAB or Python graphs, and we've pretty much taken screenshots from Condor, to be honest. But yeah, here's a typical polar curve for a typical sort of top-end competitive glider being a JS1. And as we can see, it's got two axes. On our x-axis, we've got indicated airspeed, in this case in kilometers per hour. And on the y-axis, we've got our sync rate. At a glance, so if we look at this graph, we can see a few things. So obviously, as we fly faster, we start sinking faster. And our sync rate increases almost parabolically. And yeah, sorry, I think there you go. We're not going to consider the slow end of the graph, so that's out of the picture. We're not flying less than best glide, well, less than minimum sync at least in a normal competitive setting. That's very unlikely that you're going to be doing that. And the sort of left end of the graph is a typical stall. Yeah, so using the polar graph, it's when will it change? So if we look at our previous graph here, we can see it looks like that. And let's change it a little bit. And what have we done here? Well, we've added some weight. So obviously, the curve is scaled according to wing loading, which is also directly proportional to the mass of a specific aircraft. So if our plane is 20% heavier, the polar curve will scale by 20% from the origin. So if our best glide was at 100 kph, it will then be at 120 if we up our wing loading by 20%. But interesting about that as well is because it's scaling, your LD remains the same. So even though I don't know if you can see my mouse, even though we're flying faster and sinking faster, our glide ratio is actually still exactly the same. So in short, why would we increase our wing loading and scale it? Well, it's got a big advantage in that we would want to do this because we get the same LD at a higher speed, and this is in our favor in the cruise. And there is obviously a drawback in that our sink rate is increased across the board. So if we did previously have a minimum sink of 0.4 meters, we've now suddenly got 0.6. So anytime we're not covering ground on our task, we're basically at a disadvantage. So yeah, using the polar curve. So what's of interest in this? Well, a tangent line intersecting the origin, which is the dashed line on the top left of the graph that you can see there, that basically gives us our best glide. And if it's tangent to the curve, intersects the origin, that's your best glide. And then any straight line that intersects the origin will be for a fixed glide ratio. So if you you can take that line and keep the one end through the origin and move the other end down a bit, and it'll intersect the polar in two places, and those will be your speeds at a certain glide ratio. Speed to cruise. So we can then take our tangent line and we can adjust it in certain ways to get some more useful information. So obviously we can tell this graph can tell us what our speed to fly in still air should be and what our expected cross-country speed is. Actually, interestingly enough, not many people know that. So what we've done here is if we go back, we can see that the tangent line is intersecting the origin. And if we go to the next one, it's actually intersecting at, if we look at our Macready setting on the left, 1 meter per second. So we move that intersection further up. And then we draw a tangent from there to the polar curve. And that will give us two things. So obviously, our speed to fly will be the speed at which it intersects the polar. And then if you look at our x-intercept, which is where it sort of crosses the 0 mark around about 80 kph, is our expected cross-country performance, or our expected cross-country speed. So if we're cruising, so we've got 1 meter climbs, we're cruising at 164 kph, and we can expect a cross-country speed of around 81. And if we want to sort of pump up our Macready a little bit to 4 meters per second, so that line is now intersecting, it's actually way off the chart where it's intersecting the y-axis. We'll have to fly much faster. So now we're flying at 223 kph, and our expected cross-country speed is around about 145. Cool. Alrighty. So what's next? So we can also use this with my alarm clock. Sorry. We can also use this to incorporate the extra parameters, being the air mass that we're currently in. Do we have a head or tailwind component, or are we in rising or sinking air? So here we've got our Macready 1, but with a tailwind of 30 kph, and you can see that we'd be cruising at 155 k an hour indicated, but we'd be getting a much better glide ratio, being 56. Next, we've got, okay, so for a head or tailwind component, you're going to offset your x-intercept by the wind strength. Offset it positively for a headwind. The next trick is then offset our y-intercept by the vertical speed of the air mass we're currently in. Negative for rising air. So this is actually the opposite of our Macready setting. And what else do we have? Interesting point on that, actually, offsetting our y-intercept. If our Macready is set at 1 meter per second, and we're in a air mass that's rising at 1 meter per second, that offset basically adds up to 0, because they're opposites, and we would be flying then at best glide. And here we've got, okay. So now we're working on optimizations and improvements, and what can we do differently, and what corners can we cut? So there's a few. First, we'll look at centering thermals. So obviously in any cross-country task, especially in the flatlands, you're going to be in a scenario where you climb and run. So You'll spend some time climbing, and then you'll go carry on to the next thermal. So the basic principle here is climb fewer and climb higher. Assuming it takes 3 turns, and if we say that one turn is about 25 seconds each, to center a thermal, and during this time we're only achieving about 60% of the actual thermal strength. This means that for a 3.5 meter second thermal, we lose about 15 seconds on our cross-country speed for every attempt we make at centering a thermal. So we're losing 5 seconds per turn. If we climb 1,000 meters in each thermal, so we take it all the way from the bottom to the top, and we've got there's a little bit of missing context here. I think this is for a 300k task. Yeah, there you go. If we've got a 300k task, and we want to climb, so say 1,000 meters in each thermal. For each thermal will take us 301 seconds from bottom to top, and we're going to get an average climb rate of 3.33. If we're only climbing 500 meters per thermal, we're going to be spending 158 seconds in each thermal, but our average climb rate is going to be 3.16. That's because for both of those thermals, we've spent the same amount of time trying to center them. So basically, once you've centered it, you've already made the loss of time. So rather sort of take it all the way to the top, as long as it's working, obviously. If it starts getting weaker, then that's a different scenario. So for a 300k task, on a day where we've got 3.5 meter climbs in a JS1, we'd need to climb a total of, say, 9,300 meters. Now, if we climb 1,000 meters for each thermal, we'll climb for 2,800 seconds. If for each thermal we climb 500 meters, we're going to spend more time climbing because we're going to have to take more thermals, and each one has got an overhead of 15 seconds. So we're going to climb for 2,900 seconds. 2,966. So what do we save by 3.5 meter climbs, good weather. It's like yesterday in regionals. What do we save? Well, we're saving 151 seconds of climbing time in our 300k task, and that's actually quite significant. It's 2.5 minutes. And our task speed, so obviously if we're climbing faster, it allows us to effectively fly at a higher McCready setting. Our task speed at a McCready of 3.33, which is what we should theoretically get if we're climbing 1,000 meters per thermal, would be 135 kph. And if we've got 3.1 meter thermals, we'll be flying at 132 kph. So 2.5 k's an hour, it's quite a difference. So that is centering thermals and why you should take them higher. Next, we've got sort of minimizing the impact of wind drift on climbs. And basically the gist of this is climb where the wind is in your favor. You don't really want to spend too much time climbing on an upwind leg. That's wasted time, or not wasted time, but you're actually sliding backwards along your track for all the time that you're doing that. So let's give ourselves a scenario. So say we have a 100-kilometer out and return task, 2 legs of 50 k's, and the one is straight into wind and the other one is straight downwind. And we've got 3 meters per second climbs all the way along this task. So we can take 2 strategies here. So obviously for both of them, we're going to have the same start and finish height. Strategy 1 is we're going to start 2,500 meters above our finishing height, and we're going to turn at our halfway point at 1,600 meters, which is fairly reasonable and conservative. Strategy 2 is to start at 2,500 meters above our finishing height, so the same starting height, but we're going to turn at 1,000 meters. So we're effectively climbing 600 meters less on our upwind leg. And obviously we have to make that up on our downwind leg, but we're going to see the effect that this has. So strategy 1, where we're turning high, leg 1, we spend 1,300 seconds, and I've crunched all of the numbers in this in an Excel sheet, and if anyone wants it, I'll be glad to pass it on. But basically, leg 1 takes us 1,390 seconds to reach the turn point. And of that, we're spending 440-ish thermaling and 900 cruising. Leg 2, we're actually on final glide. So it's 711 seconds just on the cruise. We don't thermal. Final glide straight downwind, by the way. That gives us a cross-country speed of 171. Obviously, that's very high for a 3-meter day, but remember, it's a short task and we're starting quite high. Strategy 2, we're going to start at 2,500 above the finishing height, turn at 1,000. So this is the strategy where we turn our turn point a little bit lower. And now my PowerPoint isn't working. Oh, there we go. Leg one, because we're turning low, leg one takes us a little bit less time. So we're going to only spend 245 seconds thermaling on the way out and then 900 in the cruise. And that gives us a total for leg one of 1,140 seconds. Leg two, obviously, because we're a bit lower, we need to do a little bit more climbing. So we're going to thermal for 177 seconds and then cruise for 720. So leg two is obviously a little bit slower this way because we've got to make up some height. But we're making that height up where we are being pushed downwind. And this gives us a cross-country speed of 176. So by turning our turn point 600 meters lower in a 100K task into the wind and then downwind, we've made up 5Ks an hour. Also quite significant. This obviously is very dependent on the glider. The lower performance the glider, the more pronounced this effect is. And in very high performance gliders, it'll be slightly less pronounced. And I think these numbers are about right for an ASW20. Yeah, so that is minimizing the impact of wind drift on climbs. Next thing we're going to look at is leveraging density altitude. And the sort of golden rule here is cruise higher as long as the climbs take you there. Obviously, if your thermals are getting weaker as you're getting higher, it's not really worth it. But as long as your thermals are strong and keep taking you up, it's better to be high. And there we've got a nice little graph stolen from somewhere on the relationship between altitude and density and air density and air pressure. So if we're cruising at 3,000 meters above sea level, our pressure there is 695 millibars, which is around about 70% of the air pressure at sea level, call it that. If we're cruising at a little bit lower, if we're cruising a little bit lower at 2,500 meters, our air pressure is then 750 millibars, which is quite a bit higher. So obviously, the air is 7.7% less pressurized at 3,000 meters, but it is a little bit denser as a result of the environmental lapse rate. So basically, we're gaining about 6.5% of efficiency in our cruise per 500 meters that we climb, which is more than 1% per 100 meters. That's a pretty good one to remember, actually, is for every 100 meters higher you are, you're cruising 1% more efficiently. So this, if we've got a 600 kg glider, like a normal sort of 18 meter fully loaded, if we're constantly cruising 500 meters higher, we're effectively carrying an additional 40 liters of ballast, or 40 kilograms. So yeah, there's a significant gain in that. Okay, our next slide would be, or our next optimization is, or this is actually not really an optimization, but it is a sort of good rule of thumb and reference table. The penalties of deviating. So this is quite a common one, and you read Reichman or anything like this, and you sort of read about 30 degrees and don't deviate more than that on a given day for a good climb. But there is a little bit more to it than just that, and basically, in essence, if you're going to be deviating from your turn point, you're flying additional distance, and if you want to make it worth your time to fly additional distance, you need to fly faster. So deviating, we're going to look at a table, or we're going to look at, imagine a task where we're flying directly along course and we've got 2-meter climbs along the way. If we want to deviate 22 degrees, so if we look at our little graph over here, that's the first set of lines, we have to fly 9% further. And because we're flying 9% further, we also have to fly 9% faster. We need, if we've got 2-meter climbs on course at 22 degrees, we need 2.4 meters. So our thermal strength has to be actually 20% better in order to justify deviating 22 degrees. Don't worry about these numbers. I have got a pretty handy reference table at the end. If we increase that deviation to 30 degrees, we've got to fly 15% faster. So our required climb is then going to be 2.7 meters per second, which is quite a big difference. If you're on a 2-meter day, to find a 2.7 meter thermal is, that's quite a bit of variation. So unlikely that it would be worth deviating even that much. And then obviously the extreme case, if we're deviating 45 degrees, we have to fly 41% faster. And our required climb, if we've got 2 meters on track, our required thermals 45 degrees off track is a whopping 4.9 meters per second. So yeah, there is a serious, you need some serious lift to sort of justify doing that. So yeah, we're sort of reaching the end, and these are some basic rules. Obviously, I have condensed this quite a bit, and there's a lot more to it that I do want to cover in a follow-up lecture. But what follow-up rule or what sort of takeaway rules do we have from this? And the first one I'd say is, as long as the thermal's working, keep climbing. And this actually is twofold. It's not just because you're getting one advantage or another, you've got two. So the first advantage you're getting is that you've already wasted the time centering the thermal, so rather capitalize on the overhead. You don't want to spend another 15 seconds at the next thermal of the same strength, unless you know that there's a much better one ahead. And you'll be cruising higher if you keep climbing in the thermal you're in. For every 500 meters higher you are, you're flying 6% faster. And what's not to like about that? The next one obviously relates to our out and return task. Turn as low as practical on your upwind turn point. And we can elaborate a little bit more on this, and I'd sort of, if anyone has anything to add, it would be cool. But these are some calculations that I haven't done, but would be interesting to know, is how much stronger than average must our thermal be to justify climbing on an upwind leg? And obviously that's dependent on the strength of the wind. If we've got no wind strength, then it doesn't have to be stronger at all. And in strong wind, we'd be looking for much stronger thermals. And then the next part is, given a headwind component strength, what is our optimal height differential for 3 turns on a triangular task? And you can imagine that as an equilateral triangle way. You've got one sort of more or less into wind leg, one more or less across wind, and then one pretty much downwind. Yeah, and also interesting or sort of important to remember there is, for every second you spend thermaling on an upwind leg, you're literally moving backwards. So make sure the climb's worth it. Here is our table of deviations against thermal strength. So this is quite a good one. So this actually is something nice to keep handy and use as a good rule of thumb when you're flying competitions, things like that. For a 10-degree deviation, you're only flying 1.5% further, which is really nothing. And in order to justify that sort of one odd percent further that you're flying, you just need your thermal to be 0.2 meters per second stronger if you're on a 2 meter day. 15 degrees, obviously you're flying 3.5% further. You need 2.1 meter thermals, 20, and now the numbers really start sort of racking up. And basically your thermals need to be 15% stronger for 20 degrees off, and 30, you need 40% stronger thermals. Yeah, and that is pretty much it. We're at half an hour now, so obviously if there are any questions, anything like that, do put it in the chat. And in conclusion, sort of what's next? Well, first one, apply these rules in your flights, see if they help you. Perceive each day differently and adjust your rules. Don't just blindly follow the rules. If you know these are all sort of meant to be interpreted as with a few parameters plugged in and not just sort of static. Don't deviate more than 30 degrees, do this, do that. So perceive each day differently and adjust your rules accordingly. And when you're flying, it's also very sort of handy to write these things down and do proper post-flight analysis. Use your CU. What did you do differently as a result of what you know, and did it help you? Did it sort of put you at a disadvantage? And what did the top pilots do differently? And that's actually the sort of the gist of cross-country flying itself, is what why did people do these things and how did they help them? And that is it. So yeah, it's been half an hour. Thanks very much to everyone who helped. Brendan for doing the technical stuff, Francois for sort of driving the whole promotion and actually getting me to do this talk, which I was a little bit nervous to do it first, but yeah, I think hopefully you've learned something, and if anyone's keen, I mean, you can follow me on my social channels, Laurence Hardman. Everything's public, and there's lots of gliding content there, and we can definitely have a follow-up. There's been much talk of sort of a few people have asked me to go into more detail on certain topics, which we will do for sure. But yeah, get in touch, and I'll see you guys soon. I hope everyone enjoyed that, and I'm going to stop sharing. There we go. Awesome, guys. And my email address, I'll actually just put in the chat. Well, actually, I'll actually just keep sharing it and let you guys leave as you go. Get my PowerPoint up. See you guys next time. So a few people have asked me if we'd be doing, or if I'd do a sort of Q&A. So I mean, if there is anything anyone wants to talk about, pop it in the chat. I can also unmute everyone, and we can sort of have an actual video discussion if need be. But yeah, if there's anything, put it in the chat. We can definitely field some questions. We got some time.